This is a Chemical Kinetics podcast about chain reactions in which the autocatalytic process of isothermal chain branching will be discussed. The last example was explosion due to the increase in temperature. How the reactions produced a rise in temperature was not specified. In this example, the temperature is kept constant and the driving force is the molecular species. The initiation reactions get the chain reactions going, usually by creating the driving force species. For example, initiation reaction can be one with no radicals as reactants, but increase the radicals as products, with the radicals being the driving force. The branching reactions are those which produce more of the driving species. For example, if the reactant contains one radical, but the products contain two, not necessarily the same radical, then the radical is a branching reaction. This type of reaction enhances catalytic action. If the same number of radicals are found in the products and reactions, then it could be called a propagation reaction. Termination steps reduce the driving force. For example, if two radicals combine to form a non-radical species, then it is a termination reaction. Using the system in the previous slide, we can write a full expression for the production of X. If we assume that the amount of fuel A is always in abundance, then we can assume the concentration is always close to the initial concentration. This is called the pool approximation, and is at least true at the beginning of the explosion. The final expression becomes an expression whose only dependent variable is X. With this approximation, dx dt is only a function of X, so the expression can be integrated to give an expression explicitly for X. And this is it here. The critical parameter phi in the exponential, and if we examine these values, we can divide the behavior into different regions. Looking at the behavior of phi, the behavior of the system can be analyzed through the behavior of X as t approaches infinity. If phi is less than 0, the termination reaction, K3, is larger than the branching reaction. This means this system will reach a stable value because termination is stronger. If phi is greater than 0, the termination reactions are slower, and the branching reactions dominate. So the value of X grows without limit. The system explodes. In the case of phi equals 0, the branching and the termination reactions are balanced, and X has a linear growth, with X equals K1 times A. This is a graph of the behavior of X versus time of the three cases represented by phi, where phi gives a relationship between the branching reaction in the term m-1 K2 A0 and the termination reaction K3. So in this case, at constant temperature conditions, it is purely the species X which determines the explosion. In a typical combustion reaction, actually it is a combination of both temperature and species which produces the autocatalytic effect. In fact, they enhance each other. As the temperature goes up, the rates of reactions increase, increasing the number of radicals of the system.